Hey guys, so this is number 12 from the Bluman ninth edition. And, okay, number 12. And this is section 7.2. Okay, so it says a thunderstorm speeds. A meteorologist who sampled 13 randomly selected thunderstorms found that the average speed at which they traveled across a certain state was 15 miles per hour. The standard deviation of the sample was 1.7 miles. Find 99% confidence interval of the mean. If a meteorologist wanted to use the highest speed to predict the time it would take storms to travel. Storms to travel across the state in order to issue warnings. What figure would she likely use? Okay, so it says a meteorologist who sampled 13 randomly selected thunderstorms. So what does that really mean? That means that the sample that the meteorologist used, it was equal to 13 just any randomly selected thunderstorms. Whenever it says sampled, or it was something that was randomly selected, this is our sample size, and our sample size is always denoted by n. This is sample size. Okay, so again, this is in this section we talk more about t distribution. And the reason why we do the t curves rather than the z curves is that we really don't have the population standard deviation. We have our sample standard deviation, which is very different than population, because the population is very general, and from the population standard deviation, you can actually just you can just use a normal z curve. But here, t curves is not just one nice normal z curve where the variance is 1 and the standard deviation is 1 and your mu is 0. Instead, here it's more like a family of curves, and the shape of the curve really depends on your degrees of freedom. So the more degrees of freedom you have, it means the more it's gonna approach the normal shape. So again, this is I feel it's clear in this figure right here. See, when here the t for the degrees of freedom is 5, it's really flat. Our z curve, the z curve actually is the most normal. It's exactly normal because it's the perfect, like you have your mu at 0, your standard deviation at 1. It is perfectly normal. Here, notice that they all have a mu of 0. However, the variance and the standard deviation for t curves varies, because again it depends on the sample. It doesn't depend on the population standard deviation, rather it depends on the sample standard deviation. And here it says that, and as your degrees of freedom increase, it's gonna approach the z curve, because look at when the degrees of freedom is 20, it looks more like the z curve. See how it's like only a little bit of it's like a little bit above it, because this is my t when here this is my 20. My difference is not that big, but look at the 5. The 5 looks really flat. I don't know why this is like that. But yeah, my 5 looks really flat. Like it looks like a really flat curve. And this just shows that as you get a bigger sample size, the more it is likely that you approach a really nice normal distribution. Okay, so I discussed what degrees of freedom are, like in a previous video, but I'll just reiterate it. Okay, I really can't say that word, but I'm just gonna say it again really quickly. Basically, degrees of freedom is if I have a certain amount of data and I need the mean to be like a certain number, I can choose any numbers I want, but at some point I'm gonna have to calculate the last number so that my numbers turn out the same every time. It's really described in more detail later, and I mean in more detail in the earlier video. But my degrees of freedom is basically how many data values that I can freely choose before I have to calculate my last value, so that when I add them all up together, and then divide them by however many there are, I end up with the same mean. So yes, this is basically it. Now, okay, so now I'm gonna solve the number 12. Okay, so it says a meteorologist who sampled 13 randomly selected thunderstorms. Okay, always my degrees of freedom, when I have my n, let's just do degrees of freedom right away so that we don't forget them. It's always going to be denoted by the equation n minus 1. So it's just going to be 13 minus 1, which is 12. This is the easy way to remember what degrees of freedom are. It's always your n, take away 1. Because you can freely choose, like, let's say I have here 13, I can freely choose any 12 numbers I want, but the last number I have to calculate it so that when I add all the numbers up and divide them by 12, I end up with the same mean. Okay, so this is good. Now I need to keep on reading to see what they gave me. So it says selected thunderstorms found that the average speed at which they traveled across a certain state was 15 miles per hour. The average speed of those 13. So this means that this is my sample average rather than my population average, right? This is my population. But here, she's only talking about the 13 that she selected. And so my average is going to be 15 miles per hour. Or I think it's MI here. Yeah. Okay, so now I know my average. And it says the standard deviation of the sample. This is probably the most important word. When they say the standard deviation of the sample, I don't have my sigma, because my sigma is for the population. I have my S. And my S here is 1.7 miles per hour. Okay, so it says find the confidence interval for 99% confidence interval. My confidence interval, CI, is going to be 99%. Now, let's talk about... Okay, so let's talk about my confidence interval. What is my confidence interval? Let's say... I have my t distribution. Again, here it's going to be the mean. It's going to be still 0, basically, because it's also symmetric across 0. But my... And just like my other one, it's going to be very... And just like my z distribution, it's going to always approach the x-axis but never really touch it. Okay, so that's good. When it says I have 99% confidence interval, that means that I am 99% sure that my data is going to be somewhere between here and here. Between these two values. And I know I just said here. We're going to calculate. It's two values that we're going to calculate later. But I am certain that my data value is going to be 99%, or I am 99% certain that my data value is going to be here. Okay. So, here, So here and here, I still need an area, right? Because remember, this whole thing adds up to 100%, which is just 1. Okay. And then here and here, I don't have my areas yet, right? However, I know that if I do 1 minus 0.99, it's going to give me 0.01, right? So this is how much area I have left after I take away this pink region. So this 0.01, right? Is it here? Is it here? Actually, it's both. Because if I divide it by 2, then I end up with 0.005, which goes here, 0.005, and 0.005 here. Okay, well, now I need to go find my t value. Okay, if I find it on the table, they're gonna be really nice about it, and they're just gonna give me my t value here, and then because it's symmetric, this one is just gonna be the negative of whatever this number is. So let's just do the table first. The table is gonna be all the way down in the book. I think these are tables. No, tables. There we go. And table B. I think it's table F if I am not mistaken. Yes, it is table F. Okay, so my degrees of freedom here, it's gonna be 12. right? So I'm gonna, here, I will go all the way down from my degrees of freedom, right, df, to 12, and I am 99% sure. So I am gonna go down, I think 12 is this one right here, yeah. And then if I go across, yeah, they meet up at this number. So I know that my t value here is gonna be 3.055 negative, correct? And here it's gonna be 3.055. I don't know why I drew this circle there. Okay, well, let's now do it with a calculator. We're gonna notice that the calculator is always gonna spit a negative number, and the reason is because the calculator understands that we're giving it the area to the left. And so if I just plug in 0.005, right, then it's just gonna give me the score right here, this score, the negative one. However, if I want the positive version of it, I'm gonna have to not only, because again, we're only looking at the left, we're not really looking at the right. It will not, no calculator will give us the area to the right. It'll never give us this area. It'll always give us the area to the left. And so if I look at this value right here, this value here, then the area to the left is everything from here all the way to negative infinity. So it's gonna cover the pink region and the other blue region right here. So that means it's gonna be 0.99 plus 0.005 to give me 0.995. And that's why the easier way to do this is just, instead of doing this big area, let's just consider this smaller area right here, the 0.005. And then even though it just gives us a negative number, all we need to do is just get rid of that negative to get the other value, because because it's symmetric. Okay, so just like last time, we're gonna do second stats. Oh wait, is it here? Or I think it's second distribution. I mean second vars, sorry. Second and then vars. And we use something called inverse t. It's gonna give me my probability. So it says here, it prompts me to put in a probability. My probability is only the area under the curve. So it's gonna be my 0.005, comma, and then my v is my degrees of freedom, which is 12. So let's enter it. Look at that. It's negative 3.0545, which rounds up to negative 3.055. So perfect. I know I did this right. Now I can move on and actually write out my confidence interval. Let's remember the equation. It's going to be my sample mean minus my t alpha over 2, which is what we just found, my t-score, times my standard deviation divided by the square root of n, and then my mu, and then my x bar plus t alpha over 2. Same thing, except now this time this is negative, this time this is positive. Oh, sorry. Okay, one thing to remember, never, even though this is negative, this is always the positive one. Always, always, always. Just take, really they should have just done like the absolute value of t alpha over 2, because it's whatever score you put, even if it's a negative one, just make it positive. Okay? So it's gonna be my x bar here, I know is 15. I think so, at least. Yeah, it's gonna be 15 minus my t alpha over 2, it's gonna be 3.055. My standard deviation is 1.7. And then my square root of n is just my square root of 13. Again, not 12, because 12 is the degrees of freedom and not my n. And then my mu, same thing goes here. It's going to be my x bar 15, this time plus 3.055 times 1.7 divided by the square root of 13. Okay, now let's just use the handy calculator. And it was asking 15, delete, minus 3.055, and then I have 1.7 divided by the square root of 13. Enter. So this gave me, my lower bound is going to be 13.559, which really is, oh, actually 9.5, so let's just round it up. It's just going to be 15.56. And then my mu, and then this is going to be 15, this is going to be the same equation, except this time I'm just going to say plus, there we go, enter it, and it's going to be 16.44. Okay, I remember there was a second part of the question. I think it was something about speed, but I cannot remember it really right now. I'll just look it up before I finish the video. So it was here, and it was number 12. Yeah, so here it says if a meteorologist, okay, if that person wanted to use the highest speed to predict the times it would take storms to travel across the state in order to issue warnings, what figure would she likely use? Okay, so she said she wants to use the highest speed. Again, this is an interval, right? So if she would want to use the highest speed, her best bet is the 16.44, because it won't be more than that. This is our confidence interval. She is 99% sure that it's going to be less than 16.44. So if she just says 16.44, then she is almost absolutely sure. I mean, you can't really be absolutely sure, but she's positive that whatever speed she calculates, that, like, using that speed, the time that she calculates would be good, so that she can issue a warning in case anything is happening with thunderstorms. Okay, so yeah, this is basically it. So if she wants to order an issue warning or whatever, she would use this figure, so that she can calculate the time that it would take before, like, it would strike a city or something. So yeah, thank you guys.